pretty poor quality, and we thought that a studio version recorded edition of the presentation would be much easier to hear and understand. So here we are re-recording this in our offices.
Hello, I'm Scott Branton. I am a senior project manager here at RAD Planning. I've got about 20 years experience in architecture. I've worked on all forms of different buildings, from small research facilities to some world-class facilities, and I am pleased to present here with you.
And I am Toby Gilk. I'm a Senior Vice President with Radiology Planning and also the President and MRI Safety Director for MedNovus. Been working on MRI design issues, radiology and MRI design issues for pretty much all of my architectural career. Among other things, I served on the American College of Radiology's MR Safety Committee and am one of the contributing authors to the guidance document for safe MR practices, the current edition, which at the moment is the 2007 edition of that document.
So for our discussion here today, we're taking a look back at this one accident that occurred 10 years ago, and now it's 10 years later, and we're looking at all the lessons that we've learned. When we look back at an MRI, we know that this is the safest modality that we have. There's accreditation, regulation agencies, there's practices set in place to assure patient safety. The equipment and the technology does nothing but improve, so I'm going to kind of take the approach that, you know what, this is a really good thing. It's all good, and I think the future looks even brighter.
Well, intuitively, that may make a lot of sense. We know that this accident did occur 10 years ago. The fact that we're not seeing news stories splashed all across CNN on a weekly basis about other MRI accidents may lead us to believe that, you know, we've identified and fixed the problems associated with this particular accident. Unfortunately, that's not quite the case. By and large, as an industry, we don't know what the lessons learned from this particular episode were, much less applied them to contemporary practice. That is true for regulatory standards, accreditation, and safety, patient safety standards as it applies specifically to MRI. And while we may not see news stories in the national media on a regular basis, that doesn't mean that MRI accidents have remained the same or declined. In fact, as you will see in just a moment, the rates of MRI accidents have actually climbed alarmingly in the recent past. And there are some specific risk factors that if we look at contemporary practice for MRI today, they make the future look pretty scary. So we're going to look at MRI safety through the lens of this one particular accident, the accident in which the young boy, Michael Colombini, died. And when we present on this particular accident, a lot of times we open with the question, what do people know about this touchstone of MRI safety? And pretty often we get 3 answers, and every once in a while we get 4. Generally speaking, folks know that there was an oxygen tank involved, that there was a nurse, or maybe it was an anesthesiologist who somehow had a role to play in this, that ultimately the boy died. And every once in a while somebody knows the geography of this accident, knows that it occurred in New York State. Well, presumably, MRI exams in the state of New York are not inherently less safe than anywhere else, so that's really not a contributing factor. The fact that the boy died, well, that's outcome, that's not a contributing factor. So if we're looking at how to prevent future accidents, that's really not going to tell us a whole lot. The fact that it was a nurse, or was it the anesthesiologist, that there was this outside clinical person, well, yeah, that might actually have something significant, a significant role to play in this overall thing. What we're left with if we've eliminated or called into question those other three factors, what we're left with is the oxygen tank. And as an industry, we've gotten very good at blaming the oxygen tank or its proxies. Now, what does this mean? If we are blaming the oxygen tank, that's pretty analogous to this little cartoon of blaming the rock. Well, the rock was thrown by a catapult that was brought to a battlefield by an army, and the catapult was built by craftspeople, made from trees harvested from a forest, so there were carpenters involved, and the stone was quarried by quarrymen and brought from that quarry, which is presumably somewhere other than where the forest was or the village where the craftspeople put it together, brought all together. Somebody wound it, somebody loaded it, somebody fired it. If all we do is blame the rock or its convenient surrogates, Joint Commission actually doesn't look at oxygen tanks. They look at fire extinguishers and ignore oxygen tanks in many cases because they had an existing standard that allowed adaptation to fire extinguishers. If we blame the rock, if we blame the oxygen tank, we miss all of the contributing factors that might be more effective and more easy to interdict than the end result. That might wind up saving providers a great deal of time and effort if we can identify some of the root causes instead of focusing attention on the rock. So all of this comes back to the context of this one accident that we are going to use as a benchmark for contemporary MRI safety. So what did happen in this particular accident? Well, the first thing, we put a face to this accident. This is Michael Colombini. This is the boy who was 6 years old in 2001 who died as a result of that accident. And that accident took place at a hospital, Westchester Medical Center. And what you're looking at right now is the floor plan for the MRI suite. The MRI scanner room itself is sort of on the left-hand side of that floor plan. For those of you who are unaccustomed to looking at architectural floor plans and might be more comfortable looking at scans of patients, just consider an architectural floor plan as a coronal view of the building with a 1 meter slice thickness. And essentially that's what a floor plan is. So the MRI exam room, the scanner room, is on the left-hand side of the plan, and it's the little bump that projects out on the left-hand side. And you can see sort of the illustration of the scanner sitting in the middle of the room there. So to the immediate right of that is the control room. Below the scanner room and the control room is a corridor that runs left to right on the plan, and on the lower side of that corridor, directly opposite from the door into the scanner room, is an anesthesia prep area. So this is this facility, the suite for the Westchester Medical Center where this accident occurred. Now let's introduce some of the key players. The yellow square represents the anesthesiologist. The blue star represents the boy, Michael Colombini. We're starting the positions here with the anesthesiologist inside the scanner room and the boy in the anesthesia prep area. The anesthesiologist actually did some initial sedation of the boy in the prep area. We're also going to show two technologists, one of whom was on duty in order to scan the boy, the second of which was filming a prior study and was sort of tucked around the corner. Well, after being given a couple of doses of sedative, because this boy was very agitated, did not want this MRI scan, he just wanted to go home. Remember, he had had brain surgery for a tumor that had been discovered quite by accident. And he's recovering from brain surgery. He wants nothing more than to leave the hospital. He is sick and tired of getting poked and prodded by needles and scans, just wants to go home. The brain surgery was deemed to be successful. They wanted to do a baseline MRI to monitor his progress over the next several years to check for tumor recurrence. because the boy was agitated, he required an extra dose of sedative to try and prepare him for the exam. They move him to the MR table. He's still agitated, gets a third dose of sedative. They're finally able to position him, get the head coil on, the nasal cannula for the delivery of oxygen, the pulse oximeter, and the technologist goes back to the control console. About this time, the anesthesiologist is noticing that the pulse oximeter readings are dropping, 99, 98, 97. So the anesthesiologist goes to the valve and the regulator on the wall to turn up the oxygen flow to the cannula. Now, those of you who are familiar with these regulators, there's a flow indicator indicating liters per minute of oxygen. It's usually a little green ball that floats in a plastic tube indicating the rate of flow. Well, in this particular case, the little green floaty ball wasn't floating. It was resting at the bottom of the indicator tube. And the anesthesiologist dialed up the valve on the regulator trying to get increased oxygen flow, but no matter which way he turned the valve, no oxygen was flowing. So the anesthesiologist goes and knocks on the window to the control room and motions for the technologist to come meet him at the scan room door. The tech circles around and asks the anesthesiologist, "What can I do for you?" Well, the anesthesiologist is very agitated that the pulse oximeter readings are dropping and that there is no oxygen available through the wall outlet for his patient. So he tells the tech in no uncertain terms, "The oxygen is broken, go fix it now. My patient needs oxygen." This tech, the one who is about to administer the exam, knows that there's a bulk storage cylinder that feeds the room oxygen, which, by the way, was done in violation to the governing building codes at the time. The tech knows that there's a bulk cylinder in the MRI equipment room, but doesn't know how the system is set up, or more importantly, how to switch out the cylinder. She, however, knows that the other tech is more familiar with the oxygen system, so she goes to the tech who is filming the prior study and asks him if he would mind switching out the tanks and fixing the oxygen system. The other tech said, "Well, if you don't know, this is the perfect opportunity for me to show you. Let's do it together." So the two of them enter the equipment room. Those of you who are familiar with MRI equipment rooms of, say, 10, 15 years ago, know that these were incredibly noisy environments. The fans, the pumps, the air conditioning system, once you stepped into those rooms, you were acoustically isolated and could not hear anything else that was happening outside those rooms. A bomb could have gone off immediately outside the room, and they probably wouldn't have heard it in the equipment room. So the two techs are in the equipment room trying to work on the oxygen tank. The anesthesiologist is getting increasingly concerned as he's watching the O2 saturation levels drop, 96, 95, and is screaming out the door for oxygen for his patient in hopes that the techs, who are locked in the cone of silence, in hopes that they will hear the calls for oxygen. Well, they didn't hear. However, at the same time, a nurse who had accompanied a prior patient down to the MR department earlier that day returned to the department to fetch something that she had left there from the prior study. She comes in, lets herself into the department, and hears the anesthesiologist calling for oxygen, yelling for oxygen. What would any professional nurse do in a situation where a doctor is screaming for oxygen, saying their patient is crashing? Well, the nurse goes and looks for it, and what does she find? She finds portable oxygen tanks in the anesthesia prep area and says, in effect, to the anesthesiologist, "You need oxygen? I found some. Here's a tank right here." The anesthesiologist takes it from her, turns around, takes one step further, and the magnet rips the oxygen tank out of his grasp and stuffs it into the bore. The oxygen tank is drawn to the center of the magnet, which just so happens to be the position of the anatomy that you're about to scan, which in this case was the boy's head. So the tank flies and strikes the boy repeatedly in the face and head, causing severe injuries. The anesthesiologist and the nurse call the code team, who rush to the MR suite. They actually are so concerned with the state of the boy's injuries as they extricate him from the MRI scanner that they wind up calling the paramedic team to assist in the transport. After several minutes of the extrication of the boy and preparing him to be transported out, the two technologists, who are unaware of any of these events, come out of the equipment room and declare that the oxygen system has been fixed. And the first thing that they see is the anesthesiologist covered in the boy's blood from pulling him out of the MR scanner, and the code team there desperately trying to intubate and resuscitate the boy before removing him to the emergency department. So this is the sequence of events immediately surrounding the accident. But in order to understand how this accident was permitted to occur, we need to drill down deeper. We need to go back in history beyond this one day and figure out what laid the foundations for this particular accident. And in order to do that, we're going to use a tool called root cause analysis. And I am no expert in root cause analysis, and I owe some credit here to my friend Bob Latino, who really coached me through this and was the engine behind the root cause analysis of this particular accident. The way that this is done is you start with the outcome. In this case, it was the fact that the boy died. And you ask, how could that happen? Well, how could the boy die? Well, he died because an oxygen tank was brought into the room. Well, how could the oxygen tank have been brought into the room? Well, the anesthesiologist carried it. How could the anesthesiologist have gotten a ferromagnetic oxygen tank? And essentially you work backwards and backwards and backwards until you get to the latent causes, the foundational elements that set the stage to allow that accident to occur. So what the industry knows about this accident broadly is that the boy was killed by being hit in the head by an oxygen tank while he was undergoing an MRI scan. Now, I apologize for the quality of these images. We've actually zoomed in on that part of the root cause analysis that the industry broadly knows. If we zoom out and we take a look at the entirety of the root cause analysis, we find that there are over 70 elements that contributed to this particular accident. And they fall into some general classifications, and we're going to look at those families of fault, of conditions that led to or supported the accident. And we're going to look at them both in terms of this particular accident, but we're going to sort of reflect on them with respect to contemporary standards. So Scott mentioned that MRI safety is all good, and I said that accident rates were climbing pretty alarmingly. Now before we really get into this, one of the things I want to take a look at is what that means numerically. In the 5 years since 2004, which was the last time that there was a decrease in MR accidents, we have seen almost a 5-fold growth in the rates of MR accidents. In 2009, there were almost 5 times as many MR accidents as there were in 2004. So while it may be easy and convenient and gratifying to identify this one accident as a fluke, as a one-off kind of thing, the fact is that we've apparently failed to apply the lessons learned for this. And if we think that the contemporary condition is scary, the future doesn't look any brighter for us. And in fact, if we look at things like the aging population, increasing use of interventional and emergent imaging in MR, more powerful magnet systems and declining reimbursements, which generally tend to result in staff cuts. The worries about MR safety are only going to grow in the future. Declining reimbursements, staffing cuts means either less qualified, less experienced, or fewer numbers of staff in the MR department. More powerful magnet systems mean greater risks for projectiles and even burn events. Increasing interventional or emergent imaging or image-guided procedures means we're bringing more clinicians and support personnel and equipment into the room with the giant superconducting electromagnet. Aging population, let's look at where we are relative to U.S. population demographics. This chart shows the percentage of the U.S. population that is age 65 and older. And you can see by the little yellow star as to where we are and how that percentage changes over the next 15, 20 years. We are right at the launching pad of the 65 plus patient demographic. Why is that important? Because patients who are 65 and older utilize MR imaging at a rate of about 2.5 to 3 times the per capita rate for those 64 and younger. So even if our population didn't change in gross numbers, the age of our population and the number of people in that 65 plus age bracket mean that the demands for MR imaging are going up. So we've got to not only get the current situation under control, but we've got to fix some of these things because the trend lines are indicating we're going to have some serious problems in the future. So one of the families of hazard that was uncovered in the Colombini accident is physical environment, suite access, situational awareness, magnetic field hazards. We're going to take a look at each one of these physical environment factors in a little bit more detail. We're going to start with 4 zones.
Well, when we look at the 4-zone diagram as laid out here in the ACR 4-zone plan, we realize that there's certain restrictions and certain specific areas that are set up specifically for the safety. Now, Westchester had the ability to create secure zones, but did not have those set in place. Now, when we talk about the zones, you'll see that there's zones 1, 2, 3, and 4. Now, zone 1, we understand is basically zone of free access. That's essentially the world, everywhere that we are standing, that you can move about freely. Now, zone 2 is moving into an area in which you have more supervised access and a little bit more restricted access into the area. This is where we would do our screening and prep and ferromagnetic quarantining and detection in order to move into a more physically restricted area of zone 3. Now, moving into zone 3 is again more physically restricted, hopefully lockable, and only accessed by someone who is letting you in that has gone through the specific protocols for screening. And zone 4, really, this is the scanning room itself, and which again has another level of restriction, physical restriction, to get into that room. By having these zones set up, it provides a cascading series of protocols and screening that allow safety so that certain objects don't get in, or certain personnel without knowledge of what can happen in these areas are allowed to come in. Now, you'll notice that this is a plan and this is a template, and as architects we love plans, but we don't like it when there's something that can be interpreted as a given way to do this, that When a lot of times when you see something that looks like a finished product, you assume that this is the one and only way that you would be able to create this 4-zone entity, but that's not necessarily the case. This is a diagram that we like a lot better as far as the fact that it is a diagram. Each facility is unique. Each facility, in the way that they are laid out, in the way that they treat patients, their numbers of patients that are coming in, the specifics of how they're scanning are completely different. Now, what this allows for is the safety zones, and you have the elements within those zones a little bit more detailed. However, it's more of a free flow diagram than it is an actual template that could be seen as just a stamp. And we don't want to rubber stamp something that has such a element of uniqueness to this. So how can we apply this to an actual place as a diagram? Well, and this is an example of applying the diagram rather than the template. One thing that you can see is there's a few arrows placed on this plan to show some movement through the spaces and through the zones. The middle top arrow that comes in and goes over to the left is the inpatient entry. Now, the inpatient is assumed to already be in zone 2 here. You have someone coming in either in a wheelchair or on a stretcher, and they are reviewed, they're looked at, they're transferred to an MR Safe gurney. They are going through this additional screening. We're looking for anything that may be on them, on what they're being transported on, implants, going through everything once again before they are allowed into the zone 3 area, which will be the spot just a little bit further to the left of the tip of that arrow, which is essentially the control room area. The northeast corner, or the top right corner that you will see on this plan, is more of an outpatient entry. You come into a waiting area, which is essentially a zone 1. There is a receptionist and a door that they will need to unlock or open that will allow you access into a zone 2 area. In your zone 2 area, you can see 4 dressing rooms, changing rooms, that are sized large enough for personal screening in there to help with HIPAA issues. There is a bank of lockers just lower and to the left of those 4 rooms to allow personal belongings to be placed outside the rooms so you're not sitting there waiting for somebody to get done changing, so you can go in and get your stuff. There's also a toilet available in this zone. Now, as the arrow kind of goes and splits off there towards the middle of the plan, you may see this kind of a darker object there that's kind of halfway over the arrow. Now, what that is this is a indication of some method of ferromagnetic detection. Now, we want to have some of this between zone 2 and zone 3. And what we've created here is a kind of a longer transition in which you are screened within the room. You are then screened for ferromagnetic devices or implants or anything that you just somehow may have forgotten to remove. And you're placed into an area for preparation, getting an IV or in some cases, maybe a sedative may be needed to settle in, but then there's a restricted access and a locked door to enter once again into the long room that's right before the MR scan rooms. This would be the zone 3 going into the zone 4. And in these cases, it's very clear that this is not just, again, a rubber stamp of a plan or a template. That's something that you want to avoid. We recommend going with the diagram.
One of the many concerns that affected the Westchester Medical Center was situational awareness. And it's easy to write off the situational awareness component of the Colombini accident as a fluke, because both of the technologists on duty got up and they left and they went into the control room and they were acoustically separated. However, I think dismissing situational awareness concerns is something that we only do at our peril. This illustration from the VA MRI design guide shows line of sight between the operator's console and the entrance to the magnet room and the patient within the magnet. Alarmingly, we see contemporary MRI suite designs where the entrance to the magnet room is off of a shared public corridor. And the tech at the console, the first time they're aware of an unauthorized person approaching the magnet room is when they see them through the observation window having entered the magnet room. So the situational awareness conditions are not unique to the Westchester accident.
This is an example of situational awareness in a fairly combined floor plan here, in showing that just because the conditions may be compact, that there is no sacrifice needed for situational awareness and being able to see everything. Now this is, I think, a really good example of being able to see everybody in the waiting room, in the preparation areas, in the bore itself. Now, just because it's a small space doesn't mean that you have to sacrifice visualization of certain areas. And I want to go back and touch again on that 4-zone that we discussed just previously. Now, the plan that you saw on the rubber stamp template, or the ACR illustration, about 7,000 to 9,000 square feet or so, if you kind of look at some of the spaces and kind of extrapolate it. The plan that we did before was again fairly generous and able to accommodate everything, but this shows an example of what you can sort of do in a shoebox, essentially. We've got about 500 to 600 square feet outside of the scan room itself and equipment room in which to put in all of our elements for our zoning and patient safety areas. Now, this accomplishes zones 1 through 4 in this small space. It is possible. You just need to get a little bit creative and work with your architect. That's what we're here for. Just challenge us. We love a challenge.
Make your architects earn their keep.
That's right.
One thing that is a challenge and a personal pet peeve is the idea that people will do what we want them to do if we simply put up enough signage. Now, this cacophony of signage that we have up on the screen is an example of what you might see in many MR suites. I think it's interesting that there has begun to be an inkling of enforcement over labeling the zones, although I don't think that there's a comparable level of enforcement or awareness of enforcement as to what the zones actually are supposed to do. But we're seeing more and more facilities that have zone signage up. One thing that I'll share as a positive thing with regards to signage, in the photograph of the MRI suite in the lower right-hand corner